Good morning. Today I want to try something a little bit different. Instead of doing two shorter videos, I'm going to try one longer video. And remember, at any point during this, you can always press pause, get up, get a drink of water, take a lap around the house or wherever you may be. And you just don't have to watch the videos all the way through in one sitting. You do need to watch them all the way through, but you just don't have to do it all at once. So today we're going to finish up section 2.4, infinite limits, and then we're going to start section 2.5. So not to spoil anything, we're just going to dive right in. So here we have the concept of one-sided infinite limits. And you've already been introduced to the idea of two-sided infinite limits, limits that approach infinity. So what happens when we just approach from one direction? So in this example, we're interested in the limit as x approaches some value a from the right-hand side of a function f of x. And in black, I have drawn y equals f of x. So as we move closer to a from the right-hand side, I've drawn in red arrows, x approaches a. And those are just x values. F of x values increase towards infinity, which I have drawn in blue arrows. And for this reason, we say that the limit as f of x approaches x as, the limit of f of x as x approaches a from the right-hand side is equal to infinity. So let's go ahead and do an example really quick. So we have here that I'd like you to analyze the limit of this function, negative x cubed plus 5 times x squared minus 6x divided by negative x cubed minus 4x squared. That's our function, and we're interested in the limit of our function as x approaches negative 4 from the right-hand side. Now, it's pretty garish to look at this. So the first step we want to do is we want to factor. So we're going to factor our numerator and our denominator. So negative x cubed plus 5x squared minus 6x divided by negative x cubed minus 4x squared is the same as negative x times x minus 2 times x minus 3, all divided by negative x squared times x plus 4. So already we can see that we can have some things that cancel out. So we can go ahead and cancel out one of our x's and our negative sign. So our negative signs and one of the x's are going to be canceled out, which leaves us with x minus 2 times x minus 3 all over x times x plus 4. So now we're interested in the limit. And because we were able to simplify, we can say that the limit of our original function negative x cubed plus 5x squared minus 6x over negative x cubed minus 4x squared. We can say that that limit is equal to the limit of our simplified function. So now it's just a question of plugging numbers in and seeing what happens. So when we go to plug in negative 4, our numerator goes to the value 42, while our denominator is negative and goes to the value 0. Well, if we have something that goes towards 0 in our denominator, we know that 1 over it is just going to blow up and blow up and blow up. And we know that it's negative, which means we can say that this approaches negative infinity. Anytime you have a fixed number, such as 42, divided by x, and x is getting closer and closer and closer to 0 in your denominator, you're always going to reach 1 over 0, and that's the same as infinity. So let's move back. Now that we've talked about one-sided limits, let's go back to our idea of vertical asymptotes. And again, it's important that you understand the concept of a vertical asymptote, which is that if a limit of f of x approaches positive or negative infinity, either a one-sided limit or a two-sided limit, then the line x equals a is called a vertical asymptote of the function f. So let's go ahead and do an example. And this example is on finding vertical asymptotes. So we have this idea already that maybe we'll get a vertical asymptote if we get a divide by 0 error in the denominator, right? We saw in the last example that we went towards negative infinity. So it implies that the function has a vertical asymptote at x equals -4. So let's go ahead and see if we can't prove in one way or another that we do indeed have a vertical asymptote. So we've got a brand new function, x squared minus 4x plus 3 divided by x squared minus 1. And we're interested in determining the following limits and finding vertical asymptotes of f. So again, we've got a polynomial on top and a polynomial on bottom. And it's pretty easy to see that when we plug in 1, we're just going to get 0 over 0. And that's not very helpful. So our very first step is going to be factor. Now I'm going to combine two steps at once and just leave it in the limit notation while I factor, and that's totally allowed, and hopefully you guys don't get too tripped up by this. So this is equal to the limit as x approaches 1 of x minus 1 times x minus 3 divided by x minus 1 times x plus 1. So we see here, we've got one copy of x minus 1 in the numerator and one copy of x minus 1 in the denominator. We can go ahead and simplify that. Say the limit as x approaches 1 of x minus 3 over x plus 1. And now when we plug in the value 1, we don't get a divide by 0 error. So we can go ahead and substitute that value in, and we get 1 minus 3 divided by 1 plus 1, which equals -1. Well, that certainly doesn't equal infinity or negative infinity, so we can confidently say there's no vertical asymptote, and I'm going to abbreviate with V dot A dot VA, no vertical asymptote at, at x equals +1. So we found the limit to be equal to -1, and we can confidently say that there's no vertical asymptote there. But let's consider x equals -1, because -1 squared is 1 minus 1 equals 0, so we definitely get a divide by 0 error in our denominator. So I'm going to go ahead and skip to our factored definition. X approaches -1 of x minus 1 x minus 3 over x plus 1, x minus 1. And here I'm not going to cancel anything out. Actually, I am going to cancel things out. So just like we did before, we're canceling out our copy of x minus 1 in the numerator and canceling out the copy of x minus 1 in the denominator. We get the same thing as before. Limit as x approaches -1 is equal to x minus 3, or is of the function x minus 3 over x plus 1. And we're interested in what's happening when we just plug in -1. Well, we're going to have to plug it in once from the right and once from the left, because -1 plus 1 equals 0. So we've got a divide by 0 error, and we can't factor anymore. So from the left, we get that our numerator approaches -4, but our denominator is negative and approaches 0. So we write infinity, because a negative divided by a negative is the same as a positive. And on the right, we get the limit as x approaches -1 from the right, x minus 3 over x plus 1. Well, our numerator again approaches -4, while our denominator is positive and approaches 0, which means we have a negative divided by a positive, we get negative infinity. So certainly because the right-hand side equals negative infinity and the left-hand side equals infinity, each of these imply that the line x equals -1 is a vertical asymptote of f. And just to kind of hone that in, here is a graph of our function. We can see we've got a missing piece right here at x equals 1. As we approach -1 from the right, we go towards negative infinity. As we approach -1 from the left, we approach positive infinity. And this is just our graph. So now let's get back to more definitions and more slides. We're actually going to change gears a little bit, and we're going to go into section 2.5, limits at infinity. So you might be thinking, well, now I've got this concept of infinity and I can make x go to some number a. Can I make x go to infinity? And you would be completely correct in that thinking. So in contrast to infinite limits, limits at infinity occur when the independent variable, usually x, it could be t, it could be u, v, whatever we want to make it, becomes large in magnitude. And limits at infinity determine the end behavior of a function. So what exactly does this look like? Oh, my bad. So let's visit our friendly function x 1 over x squared. I have it drawn here in black, and we can see that from previous, we know that as we approach 0, our function approaches positive infinity. But what happens when we take x to be infinity? So let's go ahead and use this both graphically and numerically. So in this first step, we're interested in what is x, and our x value is 10. And if x is 10, then f of x is 1 over 100, which is the same as, which is the same as 0.01. If we plug in 100, we get 0.0001. And if we plug in 1000, we get 0.000001. And on and on and on until we eventually get to the number 0. So what does this look like? Graphically, it looks like as we go over and over and over, our graph approaches 0, but it never really touches 0. And that's okay if our graph isn't evaluated at 0. It just matters what the limit is doing. And the limit as x approaches infinity goes to 0. And this brings up a pretty important discussion. And this discussion is of the idea of horizontal asymptotes. So you might be thinking, well, if I've got vertical asymptotes, I better have horizontal asymptotes to go along with it. So this happens if we've got a function f of x, and it becomes arbitrarily close to a finite number L for all sufficiently large and positive x. Then we write that the limit as x approaches infinity of a function f of x is equal to L. And in this case, the line y equals L is a horizontal asymptote. And what exactly does this look like? This looks like the following. So here I have a function, and we can see from 0 towards positive x, I'm getting, no matter how big I make my x, I approach this line L, but I never touch it. So x is getting larger and larger, and my function value is getting as close to L as possible without actually touching it. And that's the same as saying the limit of f of x as x approaches infinity is equal to L. And if we have the positive version of this, then we better have the negative version of this. So we can take x to be negative infinity. So as x gets more and more negative, -10, -100, negative infinity, my function is growing and growing and growing, but then it gets towards m and it never crosses that line. It gets as close to m as possible without crossing that line. So let's go ahead and do a couple examples. First example is going to be the limit as x approaches negative infinity of the function 2 plus 10 divided by x squared. So we can go ahead and use our limit laws to break this down. Oh, I want to be using black ink. Equals the limit as x approaches negative infinity of the value 2 plus 10 times the limit as x approaches negative infinity of 1 over x squared. So we know that this first term is going to be equal to the value 2. And the second term, anytime we get 1 over x squared, that's going to be as close to 0 as possible. So we've got 0 times 10, that equals 0. Altogether, we've got 2 plus 0 equals 2. So we can confidently say that the graph of y equals 2 plus 10 divided by x squared approaches a horizontal asymptote at y equals 2 as x approaches negative infinity. And you would see that if we plugged in positive infinity there, you'd get the exact same thing. So let's see a second example. And this is going to be for the function 5 plus sine of x divided by the square root of x. And we know that the numerator of sine x divided by x square root is bounded between -1 and 1, and therefore for x greater than 0, we can bound this using the squeeze theorem. So by the squeeze theorem, which I'm not going to show you here because it'll be a little bit too much, we know, let me break some stuff up real quick, a little bit of 5 plus the limit x approaches infinity of sine of x over root x. By the squeeze theorem, this value is going to go to 0. And because the limit of something that does not depend on x just goes to whatever its value is, we have 5 plus 0 equals 5. This means that the graph of y equals 5 plus sine x divided by root x approaches a horizontal asymptote at y equals 5. So hopefully those two examples clear up the idea of what exactly a horizontal asymptote is, and that this image is something that you can come back and reference and maybe put in your notes and help you understand. If this concept or the concept of vertical asymptotes or anything like that has tripped you up, feel free to shoot me an email. I'm always attached to my phone or my laptop or whatever, and I can always get back to you and we can set up a time to meet. I've already had a couple students drop by for office hours and it makes me feel really useful and helpful. So let's go ahead and finish up what we're working on today. So you might be thinking, well, if I can get an infinite limit, L equals infinity, and I can find a limit at infinity, that is when x approaches infinity, well, can I do them both at the same time? And the answer is yes, you can do them both at the same time. And this is called an infinite limit at infinity. So we're just combining these two ideas that we've been working with from from section 2.4 and section 2.5 to get infinite limits at infinity. And this is when, if f of x, your function, becomes arbitrarily large as x becomes arbitrarily large, then we write that the limit as x approaches infinity of f of x equals infinity. And what does this look like? This looks like the graph of f cubed, or f of x equals x cubed. So we can see here that I've got the graph of x cubed drawn in black. And as I take x to go from 1 towards infinity, the value of my function goes towards infinity, which means the limit as f of x as x approaches infinity equals infinity. And we can see the converse is true also. The limit as x approaches negative infinity, going that way, goes towards the negative infinity. So that's going to be it for today. This is just going to be the one video, so you don't have any more videos to watch after this. Hopefully this all kind of grew together into one cohesive idea at the end of it. If not, feel free to watch the video again. Feel free to send me an email. I'm always here. Bye.